Okay, so let's take a look at an example of a one sample z-test for a proportion. Now, suppose some boxes of a certain brand of breakfast cereal include a voucher for a free video rental inside the box. The company that makes the cereal claims that a voucher can be found in 20% of the boxes. However, based on their experiences eating the cereal at home, a group of students believes that the proportion of boxes with vouchers is actually less than 0.2. The group of students purchased 65 boxes of cereal to investigate the company's claim. The students found a total of 11 vouchers for free video rentals in the 65 boxes. Suppose it is reasonable to assume that the 65 boxes purchased by the students are a random sample of all boxes of this cereal. Based on the sample, is there support for the students' belief that the proportion of boxes with vouchers is less than 0.2? Provide evidence to support your answer. So now we're not estimating what we assume the population proportion is. The company claims it's 20%. So what we're going to do is see if our sample is statistically significant. And when we are looking at the statistical significance of our sample, we're answering the question, how likely is it to occur? Now, is it possible that it'll occur, or is it highly likely? Now, if it's a very small p-value, right, that means assuming the null hypothesis is true, it's a very small chance that we're going to get our result. It's highly unlikely, but we got it. That's a significant result because theoretically, it had all the odds stacked against it. Now, if we find a very large p-value, that could just be due to something like a sampling variability, right? Your sample differs from my sample, differs than the other 500 samples. So if it's a high p-value, that could just be a result of sampling variability, and chance alone, maybe we just got unlucky. So let's take a look and see, is there enough evidence to claim that the proportion is actually not 20%? So we're going to enter our phantoms model here, and you can do one of two things. You can either cut your paper into fours, and so you would do PH, AN, TO, MS, right? The state, plan, do, conclude. What I recommend is this kind of like double T-chart. So here would be your state, your plan, your do, your conclude, or each of the two letters. So I like this method a little bit better. And granted, on the AP exam, you're going to have like 2 sheets of paper for your inference question. In my class, you get the 1. So let's be resourceful here. And sorry, y'all, but I'm going to use my resources. I'm going to do some typing here. So the first thing is that we are trying to see if there's significant evidence for the parameter. So for us, P here is going to be the true population proportion of cereal boxes with a voucher. And the company claims, the null hypothesis, or the HO, is that the proportion is 20% of these boxes, whereas us as students, we believe that actually no, it's less than 20% of these boxes. So that's our hypothesis and our null hypothesis. We are trying to see if there's evidence for or against the null. Now, we weren't given a level of significance, so just to be safe, we're going to use with alpha equal to 0.05. So that's the first section there, so I'll space them out so you can see. So our parameter and then our hypotheses. So here, since we've listed the parameter, we now know that the null hypothesis is saying the true population proportion of cereal boxes with the voucher is 20%, and the alternative is saying the true population proportion of cereal boxes with the voucher is actually less than 20%. So we need to find out this evidence. Well, in order to find any kind of significance here, we need to first ensure that our conditions for inference are satisfied. So let's take our assumptions. And the first one must be that it's stated random. And we were told that we had a random sample of 65 cereal boxes purchased. And because it's a random sample, we can safely generalize these results to all cereal boxes that are similar to this type. Next up is our 10% condition, so that sampling without replacement is okay, or so that the degree of dependence among observations is negligible, which is just a fancy way of saying this cereal box has no influence on this one, has no influence on this one, etc. Now, you can write an inequality here, but again, you all know math and you all know how to read and write, so why not spice it up? So if my sample size was 65, using the 10% condition, 65 is 10% of 650. Now remember, our sample has to be less than or equal to 10% of the population. So it would be safe to assume, we can assume there are at least 650 cereal boxes in the population from which we are sampling. And then lastly, we have to do the normal check. So I'm going to do NP. And notice here now, I'm actually not looking at my sample, but I'm looking at the parameter because we assume this parameter is true. This is our base claim. So we're assuming that it actually is 20%. So instead of doing NP hat like we did with confidence intervals, we're now going to use the parameter. So here, our sample size was 65. And theoretically, we should have 20% of those 65, or about 13 boxes. And then we're also, so that's our successes. That is greater than or equal to 10. And then I'm going to try n times the complement of the success condition, which would be 65 times 0.8, which would give us 52. Both are greater than or equal to 10, and you would just write that inequality in. And so now I'm going to say the normal model is appropriate by large counts. Our success failure condition is at least 10 for both of them, so we can assume that the sampling distribution is approximately normal, making the normal model appropriate, which means we can now construct the correct test statistic, we can find the correct p-value, and our inference procedure is in fact valid. So that one is one of the more important, they're all important conditions, but that one I think is the one where students stumble most on articulating why it's important. Okay, so now we notice that our three conditions are met: randomness, independent, and normality. So we're going to say something like, since the conditions are met, we will use a one sample z-test for a population proportion, or you can write p. Oh, y'all, sorry. So I'm actually recording this video after lunch, so that's post-lunch burps, so, or hiccups. Whoopsies. Okay, so we have our parameter, we have our hypotheses, we have our assumptions, we named the test. Now let's start doing some of the mechanics or the math behind hypothesis testing. So this is where you can go ahead and cut your paper, right? So we've done the first two sections. Well, our z statistic here, very similar to a regular z, standardized z-score. We're going to do p hat minus the assumed parameter over the standard deviation of the parameter. Now, on the formula sheet, it says standard error, but here, since we assume we know the population, we're going to use these parameters here. So for us, the p hat would be our successes over the sample size, which here was 11 over 65. And again, you can leave it as a fraction or you can convert it, and I believe that's approximately 0.1692. So already off the bat, there's some evidence it's less than 20%. We know p was 20%, and normally we'd list n, but since I already explicitly labeled my variables here, we are in good hands. And whoop, all right, just hair coif check. So let us now go ahead, we would type this into the calculator, so it would list the x, the n, the parameter, and then also the significance level, I think. I actually don't know. I wish I had the calculator app on here, but we'll go over this in class. So if we were to substitute these values in, we could get the statistic by hand, or the calculator would tell you that the z-score here is going to be negative 0.6292 with a p-value of 0.2675. Now, what essentially is saying, so that's all you would need for your AP exam to get credit. So this one's just a side note here. So essentially what we're saying is if we have this distribution from this population, and we're centered at 0.2, and we have our statistic here, which was this z of why can't I write better? 0.2, and then our z statistic here of negative 0.6292. Well, since I'm saying that it's less than, this area here is going to be about 26% of the time due to sampling variability. We're going to get a result this extreme, if not more extreme. So that's just sampling variability. We don't really have any evidence that this is a rare result. It's actually a very common outcome. And so you're thinking, okay, it's very common. We do have enough evidence that it's actually less than 20%. We actually do not have enough evidence because since this is very likely every time we take, not every time, but most times when we take a random sample of size 65 from this population, there's a 26% chance we're going to get this result here. Now, it's not rare. That's not anything unusual. Actually, it's highly likely due to sampling variability. So we actually don't have enough evidence, believe it or not, to claim that the proportion is not 20%. So now we're going to bring it to the conclusion piece here. And you always have to include the context from the question. So we're going to go back here. This is now the M and the S of phantoms. So since the p-value equaled 0.2675, and that was greater than alpha of 0.05, we fail to reject the hope. And there is not sufficient evidence, and then we just restate the parameter, or the hypothesis. There's not sufficient evidence to claim that the proportion of cereal boxes with a voucher is less than 20%. And again, that's because of sampling variability, perhaps. It's highly likely each time I take these samples that they're not going to be 20%. Maybe we're just really unlucky. And even though we're very likely, we're not rare. We're not, it's not totally impossible and it happens and we like struck everyone, we're statistically significant. This is not statistically significant due to sampling variability as quite common. And we're going to talk a little bit more about this idea of p-value because it is really weird, right? You're thinking, no, it's happening a lot of the time. Why is it not significant? It's not significant because it's happening a lot of the time. So it's this weird dichotomy, but we'll continue to develop this idea throughout these inference lessons.